Hello, my name is Josh Willey. In this video, I'll be explaining how to do a problem solving for the adiabatic flame temperature. Also while solving for trying to calculate the ideal gas enthalpy at a temperature relative to 298 degrees Kelvin. And I'll be using programs like Google Collaboratory as well as Wolfram Alpha to solve for these processes. And then also, so we'll be solving using code actually after I work all these out. These derivations out to solve for the adiabatic flame temperature. Now the adiabatic flame temperature, we can explain this by, we have a system, and sorry, my markers are kind of bad. We have a system with some amount of fuel coming in, air-fuel mixture. So the fuel is made up of several components. For example, it'll be made up of methane, ethane, propane, and some amount of air. So we'll have also air as a mixture. We'll have a mixture of nitrogen and oxygen. We can't use a pure oxygen component because, for example, in welding, they have welding with pure oxygen, but that's kind of expensive. So we're going to use an air mixture of about, so let's write down the fuel is made up of, let's say, so methane, which is, let's see, it's it is CH4, ethane, which is C2H6, and we have propane, which is C3H8. And then we have our air mixture, which is made up of nitrogen which is the air is made up of 79% of nitrogen and oxygen at 21%. Okay, so this is the makeup of our air. So we can actually go ahead and write on our equations real quick. So balancing out the fuel. So our fuel for the specific methane first, so H4C, so plus some amount of oxygen going in is going to produce some amount of CO2 plus some amount of H2O as the products. Balance these out, so we have the same amount of carbons. Our hydrogens are not balanced, so I need to add a 2 over here. So that makes 4 hydrogens on both sides, but now the oxygens aren't balanced, so there's 4 oxygens on this side, so we need to add a 2 over here. So now this is balanced, now we can go ahead and add in our nitrogen. Our nitrogen is at the mixture of, so let's see, we need to add in our nitrogen, so N2, and it's at a mixture of 79 over 21. And we need to make sure that there's the same amount of oxygen and nitrogen, so we need to multiply this by 2 to balance it and do the same thing on both sides. So 2 times our 79 over 21 mixture of N2. So that's our first methane part of the fuel balanced. Actually, I need to go back real quick and actually say that this is what's going in. So our product, before I get ahead of myself, is going to be some flame. And the adiabatic flame temperature, we're trying to find out the maximum temperature of that flame coming out here based on the temperature going in and the products the fuel's burning. And we're going to say that everything is perfectly burned here. So nothing is left out. Everything is perfectly burned. This is a steady state, so it's adiabatic. There's no heat loss. There's no flow work being done on the system. The enthalpy going in is the same as the enthalpy going out. We'll get into that in a little bit. I just want to make sure we say that. So we're looking for the flame temperature, or the temperature coming out. So next we'll do the equation for ethane. So ethane is C2H6 plus some amount of oxygen goes to some amount of CO2 plus some amount of water. All right, so we balance these out. So we have 2 carbons. We need to balance it out here. 2 carbons on both sides. Hydrogen, there's 6 on this side, so you multiply this by 3, 6 on both sides now. So now we can balance out the oxygens. There's So that's 3, 4, 7 on this side. So to balance this out, we can say we multiply this by 7 over 2. Instead of having to multiply everything, this would normally we'd go ahead and put this at 14 and then scale everything up by 2. But we can just write this fraction here and it actually works for our benefit, keeping it at 7. So then now we need to balance out like we did before and put our nitrogen in. So our N2 at the same concentration of 79 over 21 multiplied by whatever is multiplied against our O2 here to keep it same. So 7 over 2. Then on that side, so we can do the same on this side. So 7 over 2 multiplied by 79 over 21, our concentration of the air, times N over 2. That's our ethane. And now we look at our propane last. So our propane is, let's see, C3H8, some amount of oxygen, produces some amount of CO2, plus some amount of water. Balances out, so three carbons on both sides, hydrogen, 8 on this side, so you add a 4 here, 8 hydrogens, 3 carbons. Now we need to make the oxygens all balanced, so there's 4 plus 6, so 10, add a 5 here, everything is balanced. Now we go ahead and do our nitrogen, so our N2, same concentration as before, 79 over 21 of the air, multiply whatever is multiplied with the oxygen, so 5 times this. Do the same thing on both sides to balance it, so 5 times our 79 over 2, or 21, times our N2. Okay, so now we have our balanced equations. All right, so this is our makeup of our fuel. So now we can actually go ahead and start looking at thinking about this in terms of enthalpy. So, like I said before, this is a steady state equation. We are looking for the temperature coming out, the final adiabatic temperature, flame temperature, where, like I said, adiabatic, there's no heat being lost. So we're going to assume that this container is perfectly insulated, no heat coming in, no heat being lost. There's no flow work being done on the process. So we can really say, and there's no mass being lost either. So we can really write the relationship that enthalpy going in is the same as the enthalpy going out. Okay, so now that we have this relationship, we can start thinking about the enthalpy of formation. Now, enthalpy of formation, we can look up the values for these individual, each one of these elements and compounds have their own enthalpy of formation. We can look it up in tables online. We can look them actually in user code. We are going to, in a little bit on Google Collaboratory, we're actually going to be using a program called CHE Tools, which we can bring in, and it'll actually give us all the properties of these different elements, including heat of formation. We can start calculating for these. So let's say we're going to be doing heat of formation for all these compounds, but just for representation, we can go ahead and say that, let's say we're looking for the heat of formation of CO2. And let's say we're looking at for a certain temperature of 298 kelvins, like I said before. And we want to raise the temperature up to a heat of formation at a temperature of 2000 Kelvin. So in order to do this, we need to add a certain amount of heat. So we're going to bring in the heat capacity. And it's going to change, this heat capacity is going to change with respect to temperature. And normally heat capacity stays pretty constant. It's one number we can look up in a table, look up online, or use programs in Google Collaboratory to actually find. But in this case, since there's such a giant leap in temperature from 298 to 2000 Kelvin, we need to actually think about, this is going to change over time, or with respect to temperature actually. So we're going to head and actually integrate this from 298 to 2000. And like I said, this is going to change so we can actually look up online and look up variables for these changing heat capacity. Like I'm going to show you in a second, I'll go into Google Collaboratory and actually bring in the CHE tools, and we'll look at actually all these different variables which we can plug into the equation, the KimCat equation, which is an online database of a bunch of information we can use to calculate our heat capacity. So I'll look up, I can write it out for you, and I'll show you in a little bit online. The ChemCat equation 107, which we'll be using, has different variables, A, B, C, and D, that we can plug in from these tables we can look up online. So our ChemCat equation 107 is actually can be written out as this. So it is A plus B times our C over T divided by hyperbolic sine times C over T squared plus D times E divided by T over hyperbolic cosine by T squared. Now this is our ChemCat equation 107. We can look this up on online, and these variables A, B, E, all these different variables, they are actually values which we can look up for individual elements. We're going to plug them in and actually solve for the heat capacity over this temperature change. So we can actually plug this in, this equation, and actually integrate these using a program called Wolfram Alpha instead of actually doing it by hand. And we can actually go ahead and simplify this down for us, make it a little easier, and plug it into our Google Collaboratory code and actually start solving out for the adiabatic flame temperature. Okay, so now we're going to start getting to the coding portion. Let's make sure that's running. And so now I've already got the code here to pull in our data from CHE Tools. And this is going to allow us to pull in a bunch of information on the contents of the fuel that we're going to be using. So we're talking about methane, ethane, propane, and different other chemicals and compounds like water. We're going to need CO2 and nitrogen and oxygen. We're going to need to pull in all that data from somewhere. So we have this code here that's going to call it in from a database. Just going to call it in, and this will allow us to get all that data. So if we go over here, we can actually see it under CHE Tools and Data. Pulls up a bunch of different chemical compounds. As you see here, we've got one of them we'll be using. We can look at, for instance, carbon dioxide. We can look here and see, okay, we've got heat vaporization. We've got ideal gas heat capacity for one. And this is actually what we'll be using a lot today. And you notice that it is in joules per kilomole Kelvin. And obviously, like I said, we'll talk about in here in a second. I'll start calling in some values, but we want to notice that it is in kilomoles per Kelvin. And we want to be working in joules per mole Kelvin. So later on, we'll have to divide by 1,000 to get it down there. We'll get that in a second. You'll notice here we have certain heat coefficients. Like I was saying before, I can go back actually, and I was talking about an equation, the equation 107 from ChemCat, which I'll look up here in a second. We actually, I wrote this down. I'll go and actually show you online where we got that. But these variables are actually heat capacities, which we call in, and we go back here. These are the actual variables in which we're calling in for each and every one of these elements I'm about to call in here in a little bit. So like you see here, we have our A coefficient, our B coefficient, C, D, E, F, and G. These are all coefficients we can call in and we can plug into this equation 107 in order to get our heat capacity, and then we're going to test it over a temperature change, in this case from 298 raised to 2000. And we're going to try to find the heat capacity, the enthalpy change, really, rather. So let's go back here and go to our notebook, and let's go start importing in some stuff here. So we've got import, let's see, import numpy as np, and we will also import, let's see, from scipy.optimize, import zeros. And this function will allow us to actually, instead of guessing for the adiabatic flame temperature, given our starting temperature of 298 kelvins, we are actually going to be able to use this to, instead of guessing it over and over through trial and error, and give us an exact about answer of the flame temperature we're looking for. We'll use that towards the end of this. And then we're going to go ahead and use import tools.che as CHE, and then we will also go ahead and write in our gas constant. So 8.314, that's just off the memory, and its units are joules per mole Kelvin. And like I said before, I was talking about, we can go back here and see, like I said before, the gas heat capacity. We saw that this is actually in kilomoles, not moles, which we're using here in our gas constant. So, like I said before, we're going to have to divide by 1,000 in order to get our values where they need to be. Okay, so we're going to run this. All right, that works. And let's go ahead and get a new box down here. So from here, actually, we can go ahead and start calling in our variables, actually the compounds which we're looking to use. So we're going ahead and do P equals, let's see, it's going to be, I called in CHE, so we have our CHE dot props, and we're going to call in all the different compounds and components of our fuel, as well as the air that we're going to be using. It is an air-fuel mixture coming into the for this reaction. So we're going to call in methane, so we need to spell it correctly. Methane, capital E. All right, and then we're going to do ethane. Let's see if I need to make sure I put these on asterisks here. So ethane. All right, the next one would be propane. And then the next one is going to be nitrogen. Then the next one is going to be oxygen. And then we're going to call in next carbon dioxide. Carbon dioxide, make sure I spell these correctly. And then lastly, we're going to call in water. Make sure that's capitalized. All right. So I believe I have everything here. So call this in. All right, sweet. So now if I wanted to look up certain things about our components here, I can actually go ahead and say, let's look up our, we were talking about before in their equation, if I can pull the picture back up, we were actually looking at our enthalpy of formation. So let's actually go ahead and look up the random, I can pull up the enthalpy of formation of all of these. So HFIG. If I run this, you can see here it brings up the enthalpy of formation of all these different compounds and components of our fuel and air as well. So you see we have a negative 74,850, and these are all in terms of, if I go back here, heat of formation. Here, the ideal gas heat of formation, and you can see here for carbon dioxide, it's negatives. It's a big, large number in negatives, British thermal units per pound mole. And these are negative because it's a key point that it takes energy to make these bonds. So we're doing this actual fuel combustion here. We want to realize that bonds are being made, and it takes energy to make those bonds. So we, for instance, we have like carbons and oxygens coming together to form CO2, and it takes, in this instance, it takes energy, joules, well, it's in British thermal units, but it takes energy to create those bonds. So if we go back here, so now we can start thinking about, since I've brought up before in our derivation before in the video before, I believe I showed, and we want to start thinking about the, let's see, we want to start thinking about the equation 107, also heat of formation, or enthalpy of formation, heat tank heat. So let's go ahead and actually look up the equation we're going to be using. So the equation, ChemCat equation 107, you can look it up online, and it's in a physical properties user guide here. And it actually shows me right here, these different variables are actually heat capacity coefficients. And I believe I showed you at the beginning of this video that if we want to look down at the bottom, heat capacity, let's see if we can find it again. Solid heat capacity here. Yeah. So these numbers down here at the bottom, in this case for carbon dioxide, each one of the elements we've called in, methane, ethane, they all have their own coefficients for heat capacity here for a gas. And this is the first one's your A, your B coefficient, C, D, E, F, and G, all the way down here. Each one of our gases or components have their own version of this. So we can actually call these in and plug them into our equation 107 here. You can see we have an A, B, C, an E, a D. We can plug them in, and we're going to, like I said before in this image, our heat capacities, this shouldn't be a plus here. It should be multiplied by the change in temperature. I'm sorry about that. And just call a mistake there. And we are going to, since there's a change, such a large change in temperature here in Kelvin, this thing is not, our heat capacity doesn't stay constant, so it changes. So we are going to use these coefficients to represent the change in the equation 107. We're going to use a program called Wolfram Alpha and actually integrate this over this temperature change from 298 to 2000 Kelvin and integrate it for us. And we can actually plug it back into our code and solve for this temperature change. And then eventually we'll be able to plug it back up in here into this part of the equation once we've solved for this part in terms of this integrated over this temperature change, and we can start solving for this. So let's go back and actually plug this equation into Wolfram Alpha. So we already know the, if we integrated A here, it's going to be terms multiplied by T, our temperature. So if we multiply this here, we can go ahead and say that, let's say, so it's C divided by T over, this is hyperbolic sine times our C divided by T squared. All right, so let's actually go ahead and write that in. So we have, on top, we have C divided by T. Let's write this in small. C divided by T divided by hyperbolic sine, so sine times C divided by T. Do that and do this to the second power. Let's give that a run. Let's see if it actually gives us something here. Let's see. We believe we have hit a problem here. Maybe we need to make this positive here, so a large. Let's do it again. Let's see if we can get this to work. Okay, so I think I've figured out what is going on here. So I need to add in an integration here, integrate, and then I also added in a comma T, which will help us with integration, and it threw us out a formula here. So this is actually what we're looking for. So C, or C coefficient for our heat capacity times our hyperbolic cotangent times C over T plus a constant C. And that is our first here, and we can actually plug and go in for our second part. So that was our this is our first part, our B coefficient times this first section. So now we can do the second section, and it's with an E, and it's with a hyperbolic cosine. So if we go back and substitute in, say, E, and then let's do cosine here. All right, and integrate. Let's see what happens. All right, and here we have it. And we notice there's a negative sign here. So it's a E coefficient times a negative E coefficient times our hyperbolic tangent E over temperature. So we can take these and actually plug them in for our values up here and integrate them over 298 to 2000 and actually help us solve a little more. So let's go back to our code here. And if you notice, I actually already have the code pulled up. So let's go ahead, and I already pre-wrote a function that's going to help us solve for this. Let's do code and pipe paste. Okay, so this code, this function actually rather, is going to help us find. It's going to help us find the change in enthalpy, sensible enthalpy over from ideal gas over a certain temperature. So, like I said before, for this we have our heat capacity for A times T, or A coefficient times temperature. So here, plus our B coefficient times our heat capacity times our first section right here is our first section we found using Wolfram alpha. So right here, integrated along with, and here's our negative D times our E coefficient and our tangent, and everything is divided by 1,000. Here you'll notice. So this section right here we got from the integration of our right part, which was negative tangent. And you notice everything is divided by 1,000 because I said before it was in terms of kilomoles, and we want it in terms of moles, so we divide it by 1,000. Okay, so after this, we can go ahead and start thinking about, okay, we want to, let's actually go ahead and do the actual equation. So I believe before we said we were doing it over 298 to 2000. So let's do that. So our delta heat sense of an ideal gas for, let's say, 2000, subtract delta H sense of an ideal gas for a temperature of 298. All right, and let's run this and run this, and there you go. It actually gives us the change in the enthalpy for the ideal gas at that certain temperature. Okay, so now that we've done this, we can actually start thinking about the type of fuel that we have, the components, the amount of moles we have, because the ultimate goal is we're trying to find the amount of enthalpy going in and the enthalpy going out. We want them to be the same. We want to find those enthalpies. So in order to do that, we need to find the components of our fuel. We need to find the number of moles of our fuel. So we need to actually determine that. So let's go over here and look at our chemical equation. So right here is for our top one, we have our methane. We have our ethane in the middle and our propane. So we want to actually determine the amount of moles we have of these values here. Let's go ahead and say in fuel, this is what I'm going to name our fuel, is equal to, let's see, it's equal to an array. So np dot array. And we'll say that for our methane, we'll do 10 moles. And then for ethane, we'll do 1.5 moles. And these are already predetermined values for the particular problem of ethane. And then we will do 1 mole for propane. Okay. So we have that. And actually, before we do anything, let's bring this down. So we have that called in. And actually, we want to define our fuel function. So let's do fuel function. Can't type today. Function, and let's do it equals another array, so np dot array. And we actually want to put in the chemical values for our equation. So the number of carbons and number of hydrogens in our methane, ethane, and propane that we're using here. So we will go ahead and do that, and we'll say that, what was it? So there was, for this particular one, there was 1 carbon and 4 hydrogens. So let's do 1, 4, or no, 1, 4. And then for the next one, we're going to do, let's see, we're going to do, the second one was for ethane, it is 2 to 6. So 2, 6 to come out. And then for the last one, it was for propane, and that is 3 and 8. Okay? There's a problem here. Invalid syntax. So we need to actually have commas in the middle here. All right, now let's run it. There still seems to be a problem here. So fuel function is an array. Okay. So now I think I figured out the problem. So first of all, for the sake of this, isn't really a function, it's more of a formula. So I'm gonna formula, and then problem I believe I'm having here is I need to put all of these in brackets. And now let's get around. Now it works. Okay, so I had an improper syntax there. I'll figure it out. Okay. So now we want to do, let's say we want to find the number of moles total of, say, carbon and hydrogen. All of our methane, ethane, and propane are comprised of pure just carbon and hydrogen. So we want to find the total of those. So actually the way we can find those is by, these are all matrices. So if we wanted to find them, we can actually do matrix multiplication, which in this is done with in Python or Google Laboratory, is done with an @ sign. So let's say we wanted to do in fuel. So fuel with an @ sign, so multiplying these both arrays. Fuel formula. Fuel formula. And say that. And it actually gives us these two numbers. So right here on our left is the number of carbons, so 16 moles of carbon, and the number of hydrogens we have. Okay, so let's say we want to give these values proper names. So let's say we want to set them equal to, I don't know, let's say we want the first value to be the number of carbons. So say in carbon and in C and in H. So now we do that, we can already assign those values. Let's go down below and actually start thinking about, okay, now that we know this, we can start thinking about, okay, let's think about the number of moles of CO2. So the number of moles of CO2 are dependent on the number of moles of carbon. So actually, for all of these, for every carbon there is of CO2, or number of CO2, there's a number of carbons. You see here, so we can say that, okay, in CO2 is equal to the number of carbons. Say we want to find the number of moles of water. So look back at our table again, our formulas, and we see that for every 1 mole of hydrogen, there is half the number of hydrogens. So we can say that, okay, the number of moles of H2O, or water, so H2O, is equal to number of hydrogens divided by 2. Let's say we want to find the number of, let's see, we want to find the number of carbons. No, we already found the number of carbons. Oxygen, for instance. So the number of moles of O2 is equal to, well, we look back here, number of moles of oxygen is equal to the number of moles of carbon plus the number of moles of H2O divided by 2. So let's go ahead and write that in. So number of moles of carbon plus the number of moles of H2O divided by 2. Put that all in parentheses so syntax doesn't get mad at me. And then lastly, let's say we want to find the number of moles of nitrogen. So number of moles of N2 is equal to, now we know from our equation, number of moles of nitrogen is equal to the 79 divided by 21 times, for each one of these is dependent on the oxygen, so the number of moles of oxygen in that particular equation. So we write that is, okay, we can say that it is 79 divided by 21 multiplied by the number of moles of O2. Put that in parentheses real quick. Okay. Great. Let's see if that runs. All right. Sweet. So now, let's see what we can do here. So next step is going to be, so yeah, we're going to want to do next is find our composition of our feed input as well as the product output. So let's go ahead and do that. So let's say, so P dot H I G. We'll go ahead and start that again. Okay, so we have that value here. We'll use that in a second. Start a new thing here. So we can use the function of concatenate. So concat innate. And we can take and add and combine the array for N fuel. So we can say N fuel, which we already know the number of moles of its components of methane, ethane, and propane. And then next we want to add our numpy array, so a new array of the components we want to find. Okay, we want to know the number of moles of O2. The moles of O2, come on now. O2. And then we want to know the number of moles of nitrogen. So number of moles of nitrogen. And then you'll notice here that the number of moles of carbon dioxide and water are actually 0. So we can plug in zeros for those. And 0. Okay. And this is our input, so our feed. So we can actually say in feed is equal to this. And I don't think the syntax is correct on this. Does that finish everything here? So yes. I want to put that. I think that's correct. Let's do that. So if we go down here to another box and put in feed, we can find the number of moles of all our components here. So you'll see here we have 10 for methane, 1.5 for ethane, 1 for propane, and then you have our 30.25, and here are moles for oxygen and for our nitrogen, and 0 and 0 like before, like it showed for our carbon dioxide and water. So that's our components of our feed, our input. So now we actually want to find our output. So let's go ahead and copy this and paste it out below so we don't have to type it all back in. And let's give it a different name. So this is our output, we'll call it. So let's call it out, and we want to change a few things. So for our problem, we said that we want to make sure everything is completely burnt. So our inputs, our methane, our ethane, and our propane, are completely combusted. They are burnt up. They are used in the reaction, going towards to make the temperature, the adiabatic flame temperature. So we want to actually take out the number in fuel here. It's not going to be the same. So it's going to be a similar thing. So MP dot NP dot zeros like our in fuel. This will create a list that is a list of zeros that is the same shape of our original in fuel. And we'll leave that there, and then we will want to go ahead and change a few things. So what we're looking for now is the number of moles of, let's see, in CO2. And then we're looking for the number of moles of H2O, which is produced. All right. And all the oxygen is actually used up in this reaction, so we can put a 0 here. All right, I believe this looks good. And there we go. So from this point, we can actually go ahead and start thinking about, let's go down here and delete this. Go ahead and start thinking about looking back up here. So before, we created a function that allowed us to find the change in enthalpy for an ideal gas, change in enthalpy for an ideal gas at a certain temperature. So we have our heat capacity, turbine heat capacities here. So we really want to start create a function that can take this concept down here, and we can import or input our concentrations of our feed and our outputs and allow us to find the change in enthalpy, or just find the enthalpy for these different values. And in turn, that will allow us to be able to lead us towards the adiabatic flame temperature. So we'll go ahead and start doing that. So let's go up here. Actually, before I forget, I noticed there's a problem here. So this would be roots, or root, not zeros. I noticed that a little bit ago. Okay, so here, let's see. So we're going to want to start a new code, and let's define it as HIG, and we'll put it in terms of number of moles and temperature. We'll go down, and let's see. So now we can go ahead and start, let's see. So now we're going to, I think we're going to create a function that is going to allow us to calculate the enthalpy of formation as well as the enthalpy of a mixture at a given temperature. So I'm going to add a colon here, and we're going to do this in terms of dot product of each. So NP dot product of, let's see, well, we need to do this in terms of the number of moles of concentration. So number of moles, and then the P dot HFAG. Okay, take this and then add, all right, a dot product of this. We can copy and paste this up here. Copy, paste this up here. And this time we're actually trying to find the temperature from 298 to a given temperature. This is where we're going to try to solve for the adiabatic flame temperature. So we're going to do all of this in terms of this. And we'll do here and add a number of moles. And we'll do NP dot product. Okay. And all this will do return. And run it. Okay, so that works. So now we can actually go down here and take this right here. Let's copy and paste it. So copy it. We'll go down below. That's not what I wanted to do. Here, let's create a new cell. Let's paste this. And we want to do a dot product of, let's see, we want to do a dot product of our feed. So in feed at a given temperature. In this case, let's do 298. 298. That's not what I wanted. Okay. So, I seem to have made a mistake here. Okay, so I see my problem here. This needs to be HIG here. Now let's try it. All right, so now it gives us our enthalpy here of our feed. So now we actually go ahead and let's try and find our enthalpy of our output. So in out, and I guess the same, start off with the same. 298 kelvins, put that back. All right, way off, as you can see here. So let's give it a larger guess. Let's go 2,000. We're getting closer. There we go. Yeah, there we go. We're getting closer. Let's give another guess. 300. 2,300 maybe. Keep doing enter there. I don't want to be. Yeah, see? So we're getting relatively close here. So the whole point of me fixing this earlier too, but importing this root here, is that actually we can create a function that's going to allow us to, instead of guessing and doing trial and error, we can actually solve for the exact enthalpy, temperature, flame temperature that we're looking for, and get these to match up. So we can go down here and create a function, define a function called the energy equation, or just E equation. Energy equation. And we'll say in parentheses of V. Okay, and then we're going to define T as X of 0. Do that, or V of 0. And then we'll go down here and do return. And we will do our HIG, our enthalpy of an ideal gas. of our first, so in feed at our initial temperature, so 298 Kelvin, minus HIG of our in out at our guess of temperature. All right. And the last step here is all we have to do is do our root solver of our energy equation. And then in brackets, a guess for our temperature. So I'll do 298 as our guess. And there we go. So our solution converged, and we actually have our, what we're trying to solve for is our adiabatic flame temperature is exactly 2,288.7 degrees Kelvin. This is our adiabatic, this is our flame temperature of the flame coming out of it, based on the inputs of our fuel and air. So our inputs were methane, like I said many times before, methane, ethane, and propane, as well as our air mixture of 79 to 21 ratio of nitrogen to oxygen. And there we have it. Our adiabatic flame temperature, like I said before, is 2,288.7 degrees Kelvin. All right, thank you so much for watching, and have a great day.